Yes, inside of your layers, we have two sets of parameters, which I might call M and B. M and B. Now, I've been drawing them inside of your layers. Depending on your implementation details, you can store your parameters with the layers, or you can pass the parameters to the layers as though the layer is a function, right? In other words, you could say, y is equal to f of m, b, and x. This is one way to do it. Or you could say, if you're doing more of an object-oriented style, you could say y is equal to f of x, where f is already equipped with m and b being part of the object, right? Depending on how you want to look at it. I've readjusted my instructions for this semester. I'm suggesting we should code it up more this way. So m and b are actually going to be part of this weights matrix, and we're going to be passing that weight matrix in with x to the layer so that it can compute its output. When we do backpropagation, you'll need to pass those same weights to it again. And what will happen is this function will look at your blame. It'll multiply it by m. It will completely ignore b and compute the blame on the input or the previous layer. Does that make sense? Okay. So yeah, so you somehow stuck m and b together into a big vector that we're calling weights. And however you did that, it's now your job to undo it, to kind of figure out where m and b are in those weights in that weights vector. And yeah, that's a little bit of an encumbrance. I apologize for that, but it'll make some of the things we do in this class a whole lot easier to have it all in a big vector. And that will hopefully become clear right now. Okay. Here's a quick question. Why does the backprop function not consider b? The activation function does consider b, right? Y equals mx plus b. The backpropagation, see, I can't call that y. What should we call it? Let's call it, I don't want to call it b because b is already used. We'll call it q. And I'll call this one r. We're now doing the equation r is equal to m times q. We're saying the blame of the preceding layer is just the weights times the blame on the output layer. And one of those, I think the m needs to be transposed to make it work. The question I'm asking, this has a plus b in it, and this one doesn't. Why do you suppose that might be? Yeah. Yeah, this has to do with the calculus. Remember when we computed the gradient, constant values don't affect the derivative. And we're actually, this value is sort of a derivative itself, because remember we took the difference between the target and the prediction. It's kind of how off we were. And that amount you're off is going to end up being scaled by the weights, for reasons we'll see when we derive the math. But it turns out that the bias, the constant values you add to an equation, don't affect the derivative, and so you really shouldn't do it. There's the intuitive high-level version. We'll do the more specific mathy version later. But that's what your backprop function is going to do. It's basically going to pass the blame. So this layer is going to, you're going to pass in x, and this layer is going to say, oh, here's my output. And this layer will say, oh, well, here's my output. And this layer will say, here's my output, also known as activation. Here's my activation, because they all activate in a sequence. And then we'll blame the output layer and say, you did 3 units of badness, or 2 units of badness. And he'll say, well, it's not my fault. He gave me the numbers and told me what I was supposed to say. And then he gets 1.2 units of that blame, and then that layer will say, but it's not my fault. I only said that because that guy activated and gave me those numbers. And they basically pass the blame all the way back. See how that's very much like real life? It's kind of how a neural network works too. You set these things up so that they all do some amount of the work, and then when something goes wrong, they all pass on the blame. And then once everybody has the amount of blame, they all refine themselves, and now they're better. Yes?
If you look at a really long neural network, can you use kind of the blame to see if you need to like get rid of a layer?
Interesting question. So there is work being done in trying to develop dynamically adjusting neural networks that would kind of morph their topologies as they learn. And very interesting subject. I don't think anybody's figured out how to do it well. So I don't want to tell you that that is the answer. I bet you the answer might have something to do with that, though. So yeah, that's certainly an indicator. I don't know if anybody has figured out that if you threshold it with this value, this is the right time to add or remove a layer. That's more of an open problem than a solved one. But yeah, so great thinking. You're already moving on to research, which I love. Okay, yes?
So last time we did this derivation where we found kind of this gradient with respect to the sum squared errors.
Yes.
But when I'm reading online, a lot of things use distance, like you put in distance.
Okay.
Are we going to still use the sum squared errors?
Yeah, so we're going to use sum squared error. Usually that's going to work out to be, let's see, how can I put that? Yeah, it's actually the derivative of the sum squared error that we're going to be using to assign blame. So, for example, if we have 5 and 3, the sum squared error would actually be 4 here, because the error itself was 2, right? Well, it happens that if you take the derivative of squared error, that 2 turns into a 1, and the 2 actually becomes multiplied by it. Let's see. I think I'm going to save these details for when we actually work through the math. Right now, I want to give you a high-level intuitive I want to give you just some diagrams for what it looks like, so when you code this up, you at least have a sense of what's going on. And then we'll get back to the nitty-gritty number details sometime. Yes?
Is blame always a scalar?
We'll say yes. By which I mean, each layer has a vector of activations. So we could draw that with a whole array of circles or squares or whatever shape you want to. Let me point to this. Each layer is a vector of these numbers, right? There's going to be one blame for each unit that's activated. So you could say that the layer has a vector of blame, or you could say each unit in the layer has a scalar of blame. Let's think about it that way. So if a layer looks like this, this is a layer of units, okay? Now each layer is going to feed into the next layer, and they're going to be fully connected. This one connects to all of those, and this one connects to all of those. And don't make me connect them all, it would take too long. So instead, I'm just going to quickly scribble all over the place. But pretend every node is fully connected to every other node. And now I'm just going to erase that scriggle so it doesn't get in my way. They're all fully connected now. Every single unit is going to produce one scalar of activation. I'll write the number 2 here to represent that. And then each of these units will produce a scalar of activation. And then at the very end, we're going to blame all of these units by assigning a scalar of blame to every unit. And that blame will get passed back till they've all been blamed. And now if you look at each unit, every unit kind of has a whole vector of weights that feed into it, right? We'll take the blame for that unit, and we will take the input that came into that unit. So maybe this one outputted the number 5. And it turns out that the product of that activation, that 5 times the 3.2, the blame for the unit times the value that was fed into it, is going to be proportional to how much we need to adjust this particular weight. So we will need to know what numbers fed into every unit. We will need to know how much to blame every unit. And then when we multiply those together, that tells us how to update every single weight in the network. So we'll update all of our weights, and then lo and behold, the network will give us better values. Okay? Let us break this whole thing down into a 3-step process. These 3 steps are activate, backpropagate, and update the gradient. And our layers are all going to implement these 3 functions. And so let's talk about how it'll work. Basically, you'll have a bunch of numbers that you'll feed in as inputs into the neural network, right? Now, to compute the activation of the layer, you'll call your activate function. So activate, how can I represent this? I'll fill them in with red to mean they're activating. So these units are all activating. That means they're computing their output values, right? If it's a linear layer, it's y equals mx plus b. Then those values, let's see, actually that's confusing things. Let's just pretend these numbers are your input vector. These weights represent m. Remember y equals mx plus b. There's a whole matrix of connections because each unit on this side needs to connect to each unit on that side. That's why m is a matrix. Okay, so in computing m times x, we're really multiplying this vector by this weights matrix, which computes the next set of values. So activate is really taking the vectors of numbers over here and computing the vector of numbers that go right here. There are other types of layers besides linear layers. I'm going to introduce nonlinear layers, which will represent with these circles. And those are applied unit element-wise. So each element in this vector will be applied to the nonlinearity. Then we'll activate the linear layer, which will compute the values over here. Then we'll activate this nonlinear layer. Then we'll activate this linear layer. Then we'll activate this nonlinear layer. And finally, we'll have the outputs for the whole neural network. Did that make sense? In other words, you're going to have a for loop in your code. And that for loop is going to start at the first layer. It's going to run through the last layer. And it's just going to call activate, 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 activate. And by the time you're done, the whole network has been activated. Okay. Now that you've activated the whole network, we're going to compute the blame for all of the output units. This is done by just taking the target minus the predicted value. So if you got a 0.2 and you wanted a 0.3, nope. If you predicted 0.2 and you wanted a 0.1, then your blame is negative 0.1. Because target was 0.1 and 0.1 minus 0.2 is negative 0.1. You follow that? Okay. Once you've assigned the blame to all of the units, you will call backpropagate to assign blame to the inputs of the nonlinear layer. Call backpropagate to assign blame to the preceding part, called backpropagate again. You'll keep calling backpropagate until everything has been blamed. Then when you're all done, we'll run through a third time. And this final time, we'll go in a forward pass again. And you'll say, for every layer, you'll take the value that was fed in, multiply it by the blame, and that tells you how much to update the weights. Until all the weights in your network have been updated, and now the whole thing has been refined by one iteration.
So in one iteration, you feed the example twice?
Yes. You feed it in the first time because you need to activate all the way to the end. Although kind of, you only feed in the first half of the example the first time because you only need the features to predict how it activates. Then we're going to use the labels to compute the blame because we need to see how bad the prediction was from what we really wanted you to predict. So we apply the labels on the output end, and then we backpropagate all the way to the start. Now we've blamed everything. Finally, we're going to feed in the inputs again. Although, if you implement your layers so they have a little memory and they can remember what values were fed in before, you won't have to do any math again. The next time around, the only math you do is a simple multiplication between the blame and the inputs, and that tells you how much to update the weights.
So
Yes?
when you're doing the blame for the nonlinear and the linear layers, like at a calculus level will be the same equation of like derivatives, but like within your code will be different because some functions will have a different derivative because it's nonlinear and one will have like a linear derivative we were deriving last time.
That's exactly right. So the question was, when you implement these three functions, basically calculus will dictate how you implement each of those functions for the different layer types. The linear layer types will do what they do because that's how you implement a linear function. That's how you differentiate the linear function with respect to its inputs, and this is how you differentiate it with respect to its parameters. And the same thing holds true for nonlinear layers. Doesn't really matter what type of layer it is. Essentially, we do a little calculus to figure out how to implement these functions. In this assignment, I'm just going to tell you how to implement it. This is how you implement backpropagate for a linear layer. You do matrix times the blame. This is how you implement the update gradient method in your linear layer. You update the blame thus. Basically, you add the blame to the bias. That didn't come out right. You update the bias thus. You add the blame to it. And you update the weights thus. Blame times inputs.